Here's a rigid body kinematics question that is asking us to find the angular acceleration of, well, a rigid body, as you'll see in a few moments. Now, if you'd like to see anything similar in the future, or if you'd like to see any particular topic or specific problems on maths or physics or engineering, then let me know in the comments. Okay, so let's try to read the question and understand what it wants. So we're dealing with a hydraulic cylinder, which is this right here, and this is converting linear motion into circular motion, okay? Because the cylinder is pushing a pin A in a linear fashion, so it's pushing pin A straight downwards, and then the pin is slotted into some links, and it gives those links a circular motion, right? It imparts a circular motion to the links which are hinged at B and C. Now, for simplicity, we're just going to look at one of them because the motion for link C is going to be mirrored. Okay, so let's try to see what happens with the pin and how that's related to the velocity of the links. Okay, so here's what I'll do. I'll draw, this is the slot where the pin is, right? So we've got the slot, something like that. So this is like the zoomed in image, and the pin is somewhere in here, okay? And the velocity of the pin is clearly downwards, right? And it's constant as well. So it's always moving downwards with the same velocity. Now, how is this related to the velocity of the links? That's what we are trying to find out. So what we can do here is we can decompose this velocity into two components. One component is going to be perpendicular to the links, like this, and the other one will be parallel to the links. Okay, and we also know that this angle here, if you use a bit of geometry, you'll notice that this angle is the same as this angle theta right here, right? Which is given in this question. So we're asked to find the angular acceleration in terms of this angle theta. So that's known basically. Now, this means that this component of the velocity, which is perpendicular to the length, is v cosine theta. And that's actually the velocity we have to use. Okay, and let's try to think why that's the case. So while that pin is going downwards, it's advancing into the links, perpendicular to the links, with this velocity here. And because it's slotted there, the links themselves, so let's try to draw this again. This is going to be, for instance, the lower part of the, so this is going to be underneath that slot, right? So this is the pin, even more zoomed in, right? And we must have that the velocity of this point going downwards, going perpendicular to the length, like this, which we know as v cos theta, this has to be equal to the velocity of the link itself, right? And the velocity of the link also has to be v cosine theta. Because if the velocities are not the same, it means maybe the pin is advancing faster, which means that it's melting into the link, which doesn't make any sense. And if the link is moving faster, it means the pin is melting into this part of the link, which again doesn't make sense, right? They're too solid, they're both solid objects. So the velocity of the link is therefore v cosine theta. And I hope it's quite obvious that the velocity of the link does not have any other components, right? The velocity of the link at this point has to be perpendicular to the link because the link is hinged at point B. So if it's hinged at point B, it means the velocity of the link has to be perpendicular to the link itself, and we got that as v cos theta, like that. Okay, so that's the velocity of the link, which means that we can find an expression for the angular velocity of the link AB. Okay, and we can find that quite easily because we can use the fact that the velocity at point A, now that's not the velocity of the pin, that's the velocity of the link, right? That's equal to omega AB multiplied by this distance here, which is, I'll just call it BA for now. Okay, and let's try to find what BA is. So what we're looking at is a link which is inclined at an angle theta with respect to the horizontal, and we also know this distance here is b, meaning that this distance is b over cosine theta. Okay, so distance BA is b over cos theta. Right, now you probably noticed at this point that we're not really using Euler's formulas to solve this. We're gonna do it using a bit of geometry instead. So we know BA, and that allows us to actually find what the angular velocity of AB is. So the angular velocity is going to be the velocity of A of the length over BA, and BA is sort of like the radius here. So the velocity is V cos theta over, and BA is B divided by cos theta. So the angular velocity of AB is V over B cosine squared of theta. Right. So that tells us what the angular velocity is, and as you may notice, hopefully, it only depends on theta because V is a constant. That's what the question tells us. B is a constant as well, right? It's the distance between, is the horizontal distance between the hinge B and the pin A. And the only variable here is theta, which is changing all the time. So as the pin A goes downwards, theta is decreasing. So cosine is changing as well. Now, here's what I'll do. I won't leave the angular velocity like this because the angular velocity of BA is clockwise. Okay, and if we used Euler's equations, that would we would take this into account by default. So what I'll do is I will say that omega, I won't just write it like that, I'll put a minus in front of it, just to illustrate the fact that omega is producing a clockwise rotation, right? So we found omega as a function of theta as minus v over b cos squared of theta, right? So the only thing left to do is to find the angular acceleration. And to find the angular acceleration, we just have to remember that angular acceleration is the first derivative of angular velocity. So we're going to differentiate this here, which will give us the following. Minus v over b, right? V over b, v and b are constants, so we can just take them out of the derivative. And then we have to differentiate cosine squared. And that's going to be 2 times cosine of theta, right? We just differentiate it as a power for now. Then we differentiate the cosine, which is minus sine theta. And then we have to differentiate theta itself, which is theta dot, right? That's theta differentiated with respect to time. Now, as you'll see, we have those minus signs canceling out, and then we will end up with v over b times 2 cos theta sine theta, and then times theta dot, right? But what is theta dot? Well, we actually found theta dot already, and theta dot is the first derivative of the angle, which is the same as the angular velocity by definition, okay? So I'm going to replace this whole thing by minus v over b cosine squared of theta. So alpha as a function of theta, if we put everything together, let's see what we have here. I'll put the minus in front, then we have v, and then we have v, and then that gives us v squared and b squared. And then we have 2, and I'll write it like this, 2 sine theta cosine theta times cosine squared of theta. Now the reason I didn't write it as cosine cubed is because we can compress this slightly, and this 2 sine theta cos theta is actually the same as sine 2 theta, right? Which tells us finally that the angular acceleration of bar BA as a function of the angle theta is minus v squared over b squared, and then we have sine 2 theta cosine squared theta. And that's the expression for angular acceleration. And of course the minus in front is telling us that the angular acceleration is clockwise, essentially. It's so if we were to draw everything here in terms of the, not in terms of the vectors, but in terms of the rotations that are occurring, we would have an angular velocity like this. So that would be my omega AB, right? And the angular acceleration would also be clockwise like this, right? And that's what that minus tells us. And that's the end of the question.